Hello everyone, welcome back to the fourth lecture in our lecture series Quality Management and Applied Statistics. Today we're going to talk about common distributions. My name is Ulrich Weber and we looked at binomial and Poisson last time, so we're going to carry on talking about the hypergeometric distribution today. What is the idea of the hypergeometric distribution? Quite a mouthful, that name. Basically, we're thinking about this little balls in a bag model, and we're choosing balls without repetition. So we're not returning them, we take them out and keep them. Obviously, if you think of like a really large bag with lots of balls in, it doesn't really matter that you're not putting them back because there's so many of them. So for large bags, we're going to see that we're converging towards the binomial distribution. That's what we expect. We've got a few more variables here. So the large letters refer to the bag. So that's what's in the bag. So we've got n balls in there. Yeah, in my little model here, that's 6. 1, 2, 3, 4, 5, 6 balls in the bag. And we've got m like Mike marked ones in there. So that would be 1, 2, 3. Now, what we're doing, we're taking some out, and I put this in green. This is what we're like, that's our sample, our n sample. So obviously, n is 3 here. And the question is, how many marked ones do we get, or what is the probability of getting k marked ones? So here we've got 1 marked in our n sample. Yeah. The probability distribution, the density, or the mass function rather, because we're in discrete, is fairly straightforward. It's again the idea, we had at the beginning that the probability of an event A is just the number of outcomes divided by the total number of outcomes. So how many ways of selection do I have? Like I can, basically if I have my n sample and I want k marked ones, so I basically chose k marked ones out of the total of m marked ones. Yeah, I had three marked ones in the bag, and out in my sample came 1 marked one, so I choose 1 out of 3. There's just 3 possible ways to do that. And then I have to look at the ones that are not marked. So I also have like 3 not marked ones, and obviously I choose 2 out of them. There's 3 possibilities to do that as well. That's this term here, this n minus m are the non-marked ones. These are the marked ones. And in total, how many different samples can I get out of my bag? In total, I can take n, choose n, different ways to choose my n sample. So this is the correspondence. Nothing like super fancy. You should all be like familiar with the way we calculate this after the last lecture. Okay, let's look at it. What does it look like? And we can immediately see the similarity with binomials. So I've given you an example here. We've got 100 balls, half of them, 50, are marked, and I choose an 16 sample. Yeah, now what is the probability that I get 8 marked ones? That's obviously the highest because half of them are marked, so 21%. It's very unlikely that all 16 or none of them are marked. Yeah, just very unlikely. Yeah, quite nice centered distribution. What we can, here's the CDF. Not super instructive to look at the shape, but just for completeness. And yeah, what can we do? We can change the number of marked ones, like it's the same number of balls in the bag, the same sample size, so the whole thing shifts to the left because it's less likely to find the marked one. And just like in binomial, we find that the distribution becomes asymmetric, so the left obviously is limited to the 0. You can't get less than 0, but the distribution is open to the right, so this kind of makes this skewedness. The other thing that is interesting is what happens if we take a 16 sample when we haven't got very many balls in the bag. So we only got 20 balls, so we're choosing 16, which effectively means that we're choosing 4 that are not being selected. So that's why this distribution, although we have a 16 sample, is very narrow and only has 5 outcomes, because there's not much left, not much choice. We're almost picking every ball. And I can also change the probability here, have only a quarter marked ones, and the whole thing becomes skewed and moves to the left. So I can do lots of interesting things. It's all more or less expected how it behaves. Let's just look at the relationship with the binomial distribution. So for our sample size going to infinity, given that large n is going to infinity as well. Oh, this should actually be large n, shouldn't it? If we go to lots of balls in the bag, then we should see kind of the two distributions converge. And we're starting here with a bag with 10 balls, and I'm keeping this ratio here constant. So the marked ones are always 40%, and I'm always taking a 9 sample out of it, just to keep that constant. So here we see obviously huge difference. I'm basically only leaving 1 ball in the bag, so either it can be marked one or not marked one. So hypergeometric, let's make this in green, hypergeometric only has 2 possible results, whereas binomial, with returning the balls into the bag, we got quite a nice distribution here. Now we increase large n, and sorry, I'm going to change that on the slides. Large n is 20 now, so we've got 11 balls left in the bag, so there are already quite a few more options for hypergeometric. We see this is spreading out, somewhat getting more similar to binomial. And if we increase this, if we go to 50, then it's already quite decent. 100, getting even better. And as we get to 1,000, n equals 1,000, you can't see the difference between hypergeometric in green and binomial in blue. They're almost identical. That's exactly what we're expecting. And yeah, we could also prove it mathematically, but it doesn't really add much to the point we're making here. Okay, let's do a few exercises. So let's play poker. We've got a full deck of 52 and you get 3 cards. What are the chances of getting 3 aces? Exactly. You all knew the answer. We could calculate it in different ways as well. Basically what we're doing, we're identifying the cards with the balls, and the marked ones are those we're looking at the aces. So we've got in the bag 52 cards, and 4 are the ones we're looking at, the aces, 4 aces in the deck. And then in our sample we want to draw out 3 cards and get 3 aces, so K is 3, N is 3. Put that in the formula above and you're gonna see it's like 0.2%, so quite unlikely. Right. So hypergeometric applies really well to card games because you don't return the cards to the deck, so this is like perfect for us. So now, slightly different, Texas Hold'em. We got, for the first 3 cards, we got 2 aces and a 4. And now we're getting 2 more cards here. And what are the chances that we get a 3rd ace with the next 2? Exactly. So what we're looking at is 3 cards out. Yeah, those 3 already in our hands. So there's only 49 cards left. 52 minus 3. And there are only 2 aces left in the deck. Yeah, because we already got 2 in our hands. And now we're looking at the chance when we take another 2 cards, those 2, that there's exactly one ace in it. Yeah. And you can calculate it, it's 8%, so not too bad. Cool. Let's play Lotto. So what are the chances of choosing 4 right numbers in this game? 6 out of 49. Exactly. So literally this game is balls in a bag, so the correspondence is fairly easy to make. We've got 49 of those balls. I know which of you have seen it on television. It's quite famous here in Germany. And obviously there's 6 marked ones. They're not really marked, they're the ones that are drawn in this event. So they're kind of invisibly marked only until they get drawn. And then we, on our little paper, we mark out 6 numbers as well, hopefully the same ones. And what are the chances to get 4 of the marked ones, so 4 numbers right? And it is 0.1% roughly, so not very likely. And I don't think you're gonna win much money if you get 4 right. Okay, last example. Let's stay with Lotto. What are the chances of choosing 3 or more right numbers in this game? Yes, exactly. Now we want to use the CDF. So 3 or more. 3 or more is the same, or the probability of 3 or more is the same as 1 minus the probability 2 or less. And that's what we're calculating here, because 2 or less, that's the cumulative probability. So 1 minus, and this is capital F, yeah, that's the CDF. And well, if you don't have a table or don't have a computer where you can look that up, you can also look at probability of 3 plus probability 4 plus 5 plus 6. That would also work, but I think it's a bit more work if you doing it by hand. Okay, and yeah, obviously 2 or less, k equals 2, and we've got a 6 sample, and there's 6 out of 49 numbers. Yeah, roughly 2% chance. Good. What else can we say about the hypergeometric distribution? The expectation value is n times capital M over n, and obviously for large bags this goes to the probability in binomial for large bags, yeah, because then number capital N is so large that it doesn't matter if I pick out a few. The variance, a bit more complicated formula. If you're interested how these things can be calculated and where they come from, look it up in this book from Arag Matai. I've referenced down here. It shows you in detail. If you want to work with these distribution functions, MATLAB is big help. So HyGPDF or HyGCDF are the commands, and just be sure you get the order of those variables right. So it's not the same order that I always put them in my lecture slides. So the small n goes last here in MATLAB. Also in Excel, you can calculate a different order of variables again. Just be sure you get it in the right order to get the right result. And yeah, now we've got a clear idea of the hypergeometric distribution, and I'll see you in a couple of minutes for the normal distribution, continuous distributions.